Okay, here is an example of a buffer solution problem. This question is asking you what's the pH of a solution made by mixing 15 milliliters of 1 molar HNO2 with 0.4245 grams of sodium nitrite. And you have to realize that sodium nitrite consists of the conjugate base NO2 of nitrous acid HNO2. And so this is a buffer. And so we can use the Henderson-Hasselbalch equation to solve this problem. pH equals pKa plus the log of this ratio. So what do we need to do? We need to figure out the concentration of HA, and we need to figure out the concentration of A minus. Now we're going to see that we have some choices here. Now we have one choice. We already know the volume of the solution, and we can just figure out the moles of NO2 minus. So let's take a look. I'm given 0.4245 grams of sodium nitrite, and I can use the molar mass of sodium nitrite to calculate the number of moles of sodium nitrite. And from the stoichiometry, I know it's 1:1 in nitrite. So that means that I have 0.006153 moles of nitrite. Okay, let's take a look at the Henderson-Hasselbalch equation, because our first idea was to get the concentration of A minus. And certainly I can do that. I can take the 0.06153 moles of NO2 divided by 0.015 liters of solution and get the molarity and stick it in the equation. But there's one thing that I want to point out. And what I want to point out is that if I take that ratio, then I get mole of A minus over liters of solution divided by moles of HA over liters of solution. Now it's in the same solution, so the volume of the solution is the same. So that ratio simplifies to moles of A over moles of HA. Now, you can do it either way. The reason why I'm going to move forward with using the ratio as mole of A over mole of HA is because that's going to become much more handy when you're thinking about titrations of weak acids and strong bases, or weak bases and strong acids. So let's go ahead and put it together that way. But I still need to do one other thing then. If I'm going to do that, I need to figure out how many moles of HA there are. Well, I've got 0.015 liters and the molarity was 1, so I must have 0.015 moles of HNO2. So now I can put it together. The pH equals the negative log of the Ka, 4.5 times 10 to the negative fourth, plus the log of the ratio. And so now the moles of A minus are 0.006153 from before, divided by the 0.015. So what do I get is pH equals, here's the pKa, 3.347, minus that log of that ratio, because the number is negative, or excuse me, the number is less than 1. So the log of the ratio is negative. And so when I subtract it, I get pH equals 2.96, and then coming over to the correct number of sig figs, I get pH equals 3.0. And that's the final answer.